moving in a straight line, and we know that the location of the plane at time 0 is 10, and the location of the plane at time 10 is 97, that really, no offense to second graders, but I think a second grader could understand pretty clearly that the difference between those two locations is 87. The number's a little big for a second grader, but they understand the idea. It's not complicated. Everybody okay with that? Okay. Then what we did is we said we want to figure out how to use velocity instead of position to calculate displacement. The basic idea really is very, very simple. Here's the basic idea. If a plane has a velocity of 7 miles per minute, that means the plane's position is going to be changing by 7 miles every minute. And so if I'm looking at a 10-minute duration, the math is extremely simple. All I'm doing is saying, well, I just need that to happen over 10 minutes. So the minutes divide out, and I've computed that wherever the plane was, it should now be 70 miles to the right of where it began. So I have calculated displacement. This is displacement. This is displacement. The 87 was calculated using positions. The 70 was calculated using velocity. But they're both displacement. They're both displacement for the exact same time period. However, the obvious question is, wait a minute. It's not possible for a plane to have a displacement of 87 and to also have a displacement of 70 for the exact same time period. That can't happen. This is the perfect answer. There's no flaw in that number. It is exactly 87. That is the displacement. This number is flawed. Just raise your hand if you can tell me the flaw. Why is the 70 not accurate? It's not bad. It's close to 87, but why is that incorrect? You should be thinking in a simple way. It's not a complicated answer. Like, why is the 70 wrong? We said, hands down for a second, I want to get more hands. We said that for the 10 minutes of time, for the 10-minute flight, if the velocity is always 7 miles per minute, that means for that entire 10 minutes, every time 1 minute goes by, the plane will move 7 miles to the right. Therefore, after 10 minutes, the plane would be 70 miles to the right. There's nothing wrong with the computation. That's perfect. But the 70 is not correct. Like, the plane moved 87 to the right. Why is the 70 wrong? Hands up. There we go. Why is the 70 wrong? Jacob.
Because the velocity is changing within the 10 minutes.
Perfect. The velocity does not remain at 7 for the entire 10 minutes. In fact, the velocity is only 7 for a moment. Then, as you can see from the graph, the velocity rises. So how many knew that? 2 points, 3 for Jacob. So 70 is wrong. It's not correct. There is a very simple way to use velocity to find displacement and get a more accurate answer. You can do this. You can say, okay, well, since the velocity clearly isn't 7 for the entire 10 minutes, let's just assume the velocity is only 7. For the first 2.5 minutes. And I'm writing down units just to check. You don't have to write down all the units. That gets to be a little bit tiresome. So I go, okay, so minutes will divide out. I'll end up with miles, which is what I want, because I am trying to calculate a displacement. Well, after the first 2.5 minutes, the velocity has definitely changed. So I'm going to come over here and inspect. here's the 2.5 minute mark. So up here, it's kind of a guesstimate, looks to be about 8.2. So and we'll say that that velocity is true for 2.5 minutes. And then I just keep going. So I go to the next 2.5 minutes, and now the velocity has changed again. We're at the 5 minute mark. So now the velocity is 9.2. Keep going. Now we go to the 7.5 minute mark. Looks to be about 9.7. Like that. So now what I've done is, instead of saying the velocity is going to be 7, for the entire 10 minutes, I've done a much better job of approximating the velocity. I've said that for the first 2.5 minutes, the velocity will be 7. But then for the next 2.5 minutes, the velocity is going to be 8.2. For the next 2.5 minutes, velocity is going to be 9.2. For the next 2.5 minutes, velocity is 9.7. I've covered the same 10-minute period. I've just done it in 4 samples or chunks. I don't know what kind of word you want to use. Questions? Please.
That's an integral, right?
So this process right here, this process that's really, really simple, all you're doing is multiplying 2 values repeatedly, and then you are adding them up.
Right.
That's integration.
So integrals are just used to find displacement over time?
So I want to give Luke another ticket. 2 in 1 day is not common. Everyone listen to this answer. We are using an integral to calculate a displacement for a given time period. Absolutely. However, you can use an integral anytime you need to do any sort of computation that can be broken into small pieces and simply involves multiply, 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 add them up. And so in this class, we're going to do, I don't know, it seems like about 5 different applications of integration. There are many more. Stupid trivia, look over here. The official name for this device that I spent several years of my life working on in my previous career, this is known as a integrating sound level meter because it integrates the sound levels. So this actually performs integration.
What does that do? Or what is it used for?
So I have to tell you the price because then it seems more important. This makes me feel better about myself. Yeah, we sold this for about $4,100. $4,100, yeah.
So that's worth a lot of money.
Not anymore because it's old. You know, this is the living, breathing version. Like this is operating. That's what I'm using to record the conversation in the room. Yeah, the microphone on this thing sells for about $1,800. Like it's a very, very precise microphone. It can measure sound over a very wide frequency range as well as over a very wide temperature range. If you start investigating measurement devices, that's what you'll find out right away. You can buy measurement devices that cost $20. Like you can buy a sound level meter for like $20, $30, $40. Not $4,000. But it won't have the ability to do the measurements over such a wide range. That's where this one shines, and that's why it costs so much. That's why people are willing to pay that much. If they have an application that needs that, they'll pay it.
Is that why we can hear everyone so well on the recording?
Yes, because it's not the kind of mic you're used to using, which is like what you see in a church or something, where it's meant to just only work up close to your mouth. Like a vocal mic, like, you know, Kayla is a vocal performer. Those kind of mics are not meant to pick up very far away. They just want to pick up you. This is an environmental mic. It's meant to pick up everything. This system, not exactly this one, but a variation of it, has been installed in a few NFL stadiums around the country, actually. So when they do the whole thing, they show the noise of the crowd. They're using this type of equipment or something very similar. So anyway, useless trivia. Question? I lost track of the question. Back to Luke. So integration can be used for a lot of different things. Here we're using integration to find displacement. And what you see here, this is integration. It's just a name somebody gave to this process. The process is simple. It's just multiplying and adding. That's it. Question? Awesome. Okay. You can use your calculator throughout this entire unit, so I need you to get used to using it. Did anybody happen to do that computation? Do it quick, I'll pay you. Go. Yeah, no restriction on your calculator for this entire unit, so you want to start making sure you have it with you. Anybody have it? Luke, what do you got?
85.25.
And what are the units, Luke?
Like miles.
Yep. There's going to be a lot of points on the next test that are given for having the right units. So you've got to make sure you remember to use units. So now what we know is this. When we checked the velocity once in the 10-minute period, our computation said the displacement would have been 70 miles. When we checked the velocity 4 times in the 10-minute period, our computation said the displacement would be 85.25 miles. The perfect answer is 87, because there's no flaw there, because we know exactly where the plane is at time 0. We know exactly where the plane is 10 minutes later, so we know the displacement is 87. There's no doubt. This is just our next best estimate, found by checking the velocity 4 times in the 10 minutes. Okay, 1 figure means I understand that perfectly. I have just no doubts whatsoever. 2 means I'd like to talk a little bit more. Show me. So we got about 4 or 5 people saying talk a little bit. So Jake.
Just kind of confused. Why did we split it up between like the 2.5?
Oh, the 2.5 is totally random.
Oh, okay.
So what I did is I started out with just one velocity to represent all 10 minutes. And then my logic said, well, because the velocity is changing, that's not very accurate. So let's just check the velocity more than once. And the 4 was random. I could have checked it 5 times. I could have checked it 10 times. Does that answer that question? 3 points. Please, George.
Is the more you check it, the more accurate it will be?
Does that feel like common sense?
Yeah.
Yeah, absolutely. No, and I want it to feel like common sense because then it's easy to remember. The more we check the velocity, the more accurate we're going to get. Absolutely. 3 points, Lexi, giving her a ticket. What's the bad thing about checking the velocity more often? No, hands, come on, think. Why is it bad to check it more often, Cameron?
Does it take a lot of time?
It takes longer, right? Like we did 4 computation, that takes a little bit of time. If I check the velocity 10 times, it's going to take even longer to compute it. 3 points for Cameron. Christine, please.
So like how often should we check it?
Hold on. So Christine's question is, how often should you check it? If you want to get a perfect answer, hands up, how often should you check it? If you want to get 87, how often do you have to check the velocity when you're doing this series of computations, this integration? Sophia?
We have to check it 10 times, like for each minute.
How long?
10 times for each minute.
This is like the national giveaway ticket day. If we check it once for each minute, stay with me, Sophia, will we be checking, like will the velocity still be changing in between our checks, or will the velocity will be constant between our checks?
Oh, it'll still be changing.
Perfect. So if the velocity is changing between our samples, are we going to get the perfect answer of 87 likely, or likely still not?
No.
Does that make sense?
Yeah.
Does that feel good? So how many times do we have to check it to make sure we get a perfect answer? Reagan?
The maximum amount?
Yeah, we're back to that word we keep using in this class, right? Calculus is all about the study of infinity. We should only teach the class on Sunday, to be honest, but that was it. Good, got the joke. Right? Look up. Yeah, I'm actually serious about that. The idea of infinity is hard to wrap your head around. But we would ideally need to check the velocity an infinite number of times. Notice the time interval, that's important. Here, the time interval was 10 minutes. Here, the individual intervals were 2.5, they added up to 10. We want to get to the point where we would have time intervals that are infinitesimal in length, but when we add them up, they add up to 10. That's where it's getting hard to think about again. So we just kind of leave that hanging and then you worry about it on your own time. Okay. Question. Okay, that big idea needs to feel good to you, so we're going to vote again. If it's not feeling good, show me too. But the idea that if I want to find displacement using velocity, the only way I'm ever going to get 87 is if I check the velocity an infinite number of times. One, if that makes sense. Two, if it doesn't. Show me. 2 points for everyone. Cameron, question?
What if you're not good at guesstimating all that kind of stuff?
Oh, like reading the graph, you mean?
Yeah.
All eyes here, all eyes, come on. Okay, this fits with Cameron's question and Christine, so 2 more for Christine, 2 more for Cameron. On the actual AP test, you don't need to stress about it. What they will do is they will either craft a problem where you can find all the data you need from numbers in a table. You just have to find the right numbers. We'll do an example in a moment. Or they'll give a graph where the dots are like clearly indicated. You can just see exactly what you need. Like there won't be any estimating. Or they'll make it clear in the instructions that it's okay to estimate. You're not trying to get an exact, you just got to get close. Does that make sense? Does that answer your question?
Yeah.
Yeah, you don't have to be good at estimating. They won't make you do that. So. Yeah. Awesome. Okay, so this is integration. Let's keep going. So now, and I apologize if we're overlapping it all with what we did last time. Again, I kind of learned as the day went on a better way to make this make sense to everybody. Okay, Christine gets 2 more points. Christine's question is like, well, how do I know how many intervals I should pick? And the good news is you don't have to for this class. A mathematician by the name of Riemann, I don't know the history, he came up with a formalized method. And all you have to do is know how to follow his method. So you don't have to make any of the picks. You just have to follow his instructions. So for example, right here, item C on number 2, it says use a left. Please circle the word left. You don't really need to circle Riemann. We don't do any other types of integral approximations, so that's the only type we do. I don't know, I'd have to look it up. I just feel quite confident there are more. Like usually what happens is one person invents some idea, and then somebody else comes along and says, oh, I think I know a better way, right? They only test us on Riemann, so 2 points. This is key, so please put a circle around 4. The word equal length is crucial. Okay? And then 2 more for Cameron. Values from the table. So now I know I don't need to do any estimating. I'm just going to use the values from the table. This word is key. We are approximating this integral. We are approximating this integral. Because as we said a moment ago, ideally, to calculate the integral, we would want to sample the velocity an infinite number of times. But we don't want to spend the time required to sample the velocity an infinite number of times. So we're going to approximate the integral. So on your paper, make sure you write the integral. There are many AP questions where you get a point if you can correctly write the integral. So get the habit of doing it. In this problem, you wouldn't get a point for it because they gave it to you. But you need to have the habit. So make sure you write it. Please.
Like writing the integral with v of t multiplied by dt, like having that, right?
Mhm.
Okay.
Yeah, 3 for Andrea. This entire symbol is the integral. This symbol is just a portion of the integral. So you'd never write that by itself. It doesn't make any sense. It's kind of like writing a plus just with nothing around it. It doesn't mean anything. Does that make sense?
Does it matter, like, if you put 40 and 0 on the bottom and top, or something like that?
So it's a national ticket giveaway day. Look here. Listen. It is mathematically legal to flip them. It changes kind of what follows. So rather than kind of have to keep track of 2 different methods, I don't like to teach that just because I feel like it can get confusing since you're just learning all this for the first time. So we'll always go lowest to highest. Yeah, we'll just always go lowest to highest. We'll learn in the future that if they give us something that's highest to lowest, we have a way to adapt that. It's not a big deal. Cool. All right. You need to write approximately equal. Because we are not calculating the integral, we are approximating the integral. We also need to push the pen button. There we go. Question? Awesome. Okay, the process is, oh, yeah, please, go ahead.
Are we going to be stopped points if we don't put the approximation?
I think they're quite lenient on that. So I'm going to keep stressing that we want to get in the habit of doing it just to be safe, but I really don't think they'll dock you points if you accidentally forget. So it shouldn't be anything on your stress meter. So yeah, 2 points. Okay. Look, the integral tells us what to do. The integral tells you what to do. You're supposed to take velocity. You're supposed to multiply by, look, dt, easy, duration of time. You're supposed to take the velocity multiplied by a duration of time. We're supposed to do it from time equals 0 until time equals 40. But again, we don't want to do it for an infinite number of velocities. We're going to do it for, as instructed, 2 more for Christine, 4. Okay? So come to the table and do this. Oh, warning, big warning. Don't do this. Don't say we start at 0, we end at 40. That seems like a simple thing, but I guarantee you if you do that, it'll screw you up and you'll mess up the problem. Do this instead. Start at 0. End at 40. Like, be very precise. We are starting precisely at 0. We are ending precisely at 40. Now it's easy to break up the time into 4 equal subintervals. We go from 0 to 10. We go from 10 to 20, 20 to 30, 30 to 40. Questions?
And it has to be 4?
The instructions say 4 subintervals.
Okay, and that could just be random also?
It is random in the sense that for your purposes, you're not going to be choosing it. I've never seen an AP problem where you choose it. You just follow the instructions. Yep. Like, it can be more, but they said to do 4, so we do 4. So, 2 more for Cameron. Anybody else? Please.
They have to be equally.
Only because they told us. Yeah. We'll see problems in the future, Jonah, 2 more, where they will not say to make the subintervals of equal length, and we won't.
Oh, equal length as well. Okay.
Does that make sense?
Yeah.
2 more, please.
So if they're not equal length, do you just like you get to choose, or does the problem say how to break it up?
2 more for Jacob. The problem will specify. It's perfect. Tell me.
Sorry, what were you like stressing super hard? I didn't really catch what you were saying about, the starting at 0, ending at 40.
Oh, yeah.
Sorry, I just don't catch what you were stressing about.
No worries. So here's a cynical story. I try not to be a cynic, but once in a while it creeps out. I had a student one time during a test, test 4, which you'll take about mid to end January, came to my desk during the test. This is when we're doing the test in the room, and said, "This problem is broken." And I was somewhat offended since I created the problem. And I wanted to say, "No, you're broken." Hence the cynicism. The student had done this. They said, it says I'm supposed to have 4 subintervals. So look, Mr. Smith, we start here at 0. We start at 0. We go to 40. So the first subinterval should go to 10. And they're like, those aren't even. I'm supposed to have equal subintervals. Like the problem's broken. No, you're broken. You didn't do what I told you. I said don't ever draw bars that way. It'll play tricks with your mind. The time starts right at 0. It goes to 10. The next interval starts at 10 and goes to 20. Drawing the bars the first way just plays tricks with your brain and you think something's wrong. Does that make sense?
Yeah, that makes a lot of sense, dude.
Perfect. 3 points.
Is that because it goes like 35, 40, and then there's like 45? There could be like something on the end of like.
Well, really, I think what you're doing wrong with the bars is you're saying 0 to 10, and then 15 to 20. Well, you just left out 10 to 15. Like, it just doesn't make any sense.
So like with that interval, there's like 3 different numbers. I mean like 2 different numbers.
Yeah, listen to Christine. She's all over it
Do
today.
you have to like average them or something to find it?
Let me restate what Christine just said because it's crucial. Christine said, if we're starting at time 0 and we're going to time 10, well, in the table, there are 3 different velocities listed for that time interval. And in the graph, there's an infinite number of velocities listed. So how do I deal with that? Well, we do exactly what we did in the previous discussion. We say, for that first 10 minutes, we're only going to sample the velocity once. Okay? For the first 10 minutes, even though there are an infinite number of different velocities, we're just going to pick one because we don't want to do all those computations. Okay, I don't want to give it out loud. I want you to see it. The problem says do a left Riemann sum. So please raise your hand and tell me what makes the most common sense to pick. If they say do a left Riemann sum, I'm looking at the first subinterval. I've got all these different velocities to choose from. All these different ones. Which one am I supposed to pick? I don't know where to think of it. Janessa.
The one farthest to the left.
Which would be
7.
7. This is the best unit ever. Because really, you just talk about it enough, your brain says, well, I can remember this. This isn't hard, right? Like it just tells you what to do. I'm supposed to take velocity. I'm supposed to multiply by a duration of time. Simple. Pick the left one. So I'm going to do the units once, just to make sure I've got the right units here. So Janessa, I've picked my velocity for the first time interval. I've got to have that velocity for a certain duration of time. What would you say should be our duration of time that we're going to apply to this 7 miles per minute? 10 minutes. Because they told us to do that. They said let the 7 represent all the velocities within those first 10 minutes. Okay, we're not done yet, so we'll put a plus. But the units are working nicely because the minutes will divide out. We'll be left with miles, which is displacement. That's what we're calculating. I need a vote. 1 means this, I understand it perfectly. 2 means I'm a little fuzzy still. Jackpot, it's a sellout. 2 points for everybody. Okay. Somebody else who would like a ticket, raise. Oh, please, Jonas.
What other uses would, so when it says use left Riemann, right?
Where, Riemann, you're fine.
Yeah. Would they say like middle or like right? What other instances would they use that?
See, this is the best day ever, right? Like you guys can figure it out without me even helping.
Are you gonna hit the board again?
No, it hurt last time. Listen to Jonah, listen. You'll be tested on how to find a left Riemann sum how to find a right Riemann sum, how to find a midpoint Riemann sum. There's a fourth one that's a tiny bit more complicated, but not much. We'll talk about that later. But please, Christine.
What if there's like 4 values? Will they just not tell you to find the middle one?
You gave a ticket yet today? 2 today, whatever. Okay. Listen, it's perfect. If they will not set up a problem where as you look at the data, it is not clear which one is in the middle. They'll only give you problems where you go, oh yeah, I can see the middle's there. Is that what you mean?
Yeah.
Perfect. Zach?
Couldn't you just get the midpoint between them by adding them together and dividing them by 2 though?
That would be the average of the left and the right.
Okay.
That's actually known as the trapezoidal, which is the fourth.
Oh, cool.
Congratulations. Okay. Question.
They can have a chance since everyone was
It's coming. Cameron, what do I write next?
Would it be 9.5 times 10?
Because that's the velocity I'm going to use to represent this 10-minute period. So I multiply that velocity by time duration of 10 minutes. Cameron, what's the next one?
It would be 4.5,
Multiplied by?
10.
Somebody please do this on your calculator to make sure we're going to work this out right. Next one, Cameron.
2.4.
Okay, show me 1 or 2 if that makes perfect sense. Come on, show me. 1 or 2, does that make perfect sense? Points for the room. Okay, note that I don't do anything else. 1 second. I've got 10, 20, 10, 20, 30, 40 minutes of time accounted for. The integral said I needed to account for 40 minutes of time. I don't do anything else. I've covered the entire 40 minutes. Andrew, please.
Okay, so when we did like limits, we had to use like the symbol, like the limit symbol, like every time we did a step. Is there a reason why we don't like draw the line? Is it because it's like that one specifically means infinite in between? Or is there a reason why we don't do that?
Let me show you. I think this will answer your question. If not, you keep talking, okay? So when we were doing limit problems, what I wanted you to do is, hold on. What I wanted you to do was understand that if they say find the limit as x approaches 2 of something like this, perhaps, like that, that on the next line, we haven't found the limit yet. We've just figured out a way that will make finding the limit easier. So we factor, but we haven't found a limit. We've just found a way that will make finding the limit easier. So I still have to write limit. Does that make sense? Then I can say, oh yeah, these are going to equal 1 unless x equals 2, which I don't care about because it's a limit. So the value of this limit is simply 4, like that. That's why I had to keep writing limit.
Okay.
With the integral, this integral can be approximated by doing those 4 computations and adding them. So I'm not integrating, it's like I'm not finding another way to find the integral. I didn't say that very well. It's like I've accomplished what I set out to do.
Okay.
Like I've done what the integral asked me to do.
Okay, so you don't need to write the integral.
Yeah, in fact, ticket's coming for Andrea. Look, don't do that. I'm doing that. That drives me crazy. Like, don't do that. Okay. Okay. We're not integrating again. This process of multiplying and adding, that's what integration is. And that's why we don't have to write it again. Does that make sense? Sorry, it's fine. I don't know why I say sorry. I did it on purpose. There's something soothing, though. I think I showed this last afternoon. There's something soothing about doing this. Watch. Like if you hit the ruler if you just kind of like casual, like that doesn't, there's no, it's not soothing. This is soothing. This feels better. Okay. I just feel better. Okay, please.
So when you write the answer, do you not like rewrite that?
No, thank you. Look up, 2 more for Reagan. When you integrate, when you approximate an integral using a Riemann method, this process of multiplying and then adding, that's doing what they said to do. So just write it exactly how I've shown you. The next thing you're going to write is right here. Anybody do it on the calculator? What'd you get, Zach? 234? You always remember units. Did I give you your ticket yet, Cameron? Not yet, huh?
Oh, yeah, no, you gave it.
Oh, yeah? Good. Okay.
I could use another one, though.
Well, there's that, you know. Okay. That's how you I don't know if I'm answering your question, Reagan.
Yeah.
Okay, please.
Should it be an approximation sign?
Here's a weird thing. When you look at the AP test, like how they'll publish how they want the answers written and such. This is how they write it. And this is my interpretation of it. Mr. Ruck will help me if I'm making a mistake here. The integral itself is not equal to this series of computations because we're not doing an infinite number of computations. It's only an approximation. However, these 4 computations here, when added together, are perfectly equal to this. That's why I believe they write approximate first and then equal. And that's the best way to write it on the test to be safe. As I said to Joan, I think they'd be lenient if you don't. So,
So will an integral find some value on a curve using values from its first derivative?
say it one more time.
So will an integral find some value on a curve by using values like data from its first derivative?
I'm going to say something that we won't discuss it today, but we will later. The integral can never, so let's do a more specific example. The integral of velocity will never find a value of position. However, the integral of velocity will always find a difference between 2 positions. Is that what you meant?
Yes.
Perfect. 2 points, please.
Is there like a complex formula that like our brains can't remember, but like you could find the exact number without having to do like an infinity amount of like
Gotcha. Listen to Kayla. Okay, we won't do this until about mid-January, beginning of February. But we will eventually find a way to calculate an integral with 0 error, and we won't have to add up an infinite number of terms. So for now, we want to keep thinking. It really helps that for now, just keep reminding yourself, integration means multiply, add, multiply, add, multiply, add. Infinitely. That's what it means. Now, Newton did discover a way to avoid all that, and we'll talk about it later. So, perfect.
If we find out another way to do it, then why will they ask us questions like this on the test if we find like a more accurate way to answer?
Awesome. I say this without having done a lot of research into the idea, but I feel pretty confident that there are many, many real-world applications where you can't use the magical method. The only method available to you is this method. The sound level meter I worked on is an example of that. There was no way for us to integrate the sound levels, which is what we have to do to compute something we needed. Okay, we had to do it this way. That meter samples the sound level 32 times every second. So it's not perfect either, but that's pretty good. It's sampling how loud the sound is 32 times every second. So it gives a pretty good representation of the sound.
So one of those, you said you can buy like really crappy ones for like $20, right? Like is it just because it's a lot less accurate, like it's maybe measuring it once every second, or like maybe?
It's usually less accurate in several ways. It's going to be less accurate over temperature. So if you use it right around room temperature, it probably works pretty good. It's going to be less accurate for quiet sounds versus loud sounds. So again, if you just kind of taking a noise measurement in a room is probably pretty good. It may be less accurate over time, meaning it doesn't maintain stability very well. Anytime you buy any type of measuring device, that's what always happens. Is if you're using the device in simple, easy kind of ways, it usually works pretty good. Just when you start to extend it, it gets harder and harder. That's part of what I was challenged with in one of my projects was, I don't have a picture of it, but I took an older device. They said, well, this one works pretty good. We want to make it better. And so that's what gets challenging is how to stretch it out with these, always pushing the edges, as they say. So perfect. Anybody else? Awesome. So that's left Riemann sum. Good? Okay. This one here says, use the graph to illustrate what the left Riemann sum approximation of the integral looks like visually on a graph. Here's what we can visualize this computation as looking like. Notice, we're taking 7 miles per minute, and we are so 7 miles per minute. On the graph, this line that I'm now drawing, this vertical line has a length of 7. Show me 1 or 2 if that makes perfect sense. That vertical line has a length of 7. That vertical line has a length of 7 points. We are multiplying that vertical line's length by a duration of 10 minutes. 10 minutes on the graph is the length of this line. 10 minutes on the graph is the length of the orange line. 1 or 2, show me. 10 minutes on the graph is the length of that orange line. So as we integrate, we are multiplying 2 points for everybody. The purple line by the orange line, we're finding this area right here. Questions? Cool. Notice this. If we, in that 10-minute period, if we had checked the velocity 4 times in that 10-minute period, we would have gotten rectangles that would have looked like these. Come on. Okay, show me 1 or 2 if that makes sense. Be honest. Talk to me a little bit.
Oh, sorry.
Oh, you meant 1.
I
Okay.
just-
2 points for the whole room. Okay. So please note, look at me, Tom. Look hard. Look. This won't always happen with integration, but it does happen very frequently. This computation is an area. Okay? That computation is an area on the graph. It's this area right here. This needs a better color. This green one. So this area is that green area over there. Questions? The point I'm trying to make is that if we were able to sample more often, we would get closer and closer to computing this area. We would follow the curve perfectly. If we could sample an infinite number of times, we would follow the curve perfectly, and the integral would be computing that area between the curve and the horizontal axis. 1 or 2 if that makes sense.
Wait, sorry, can you say that again?
Huh? So this computation computed this area here in green. But ideally, if we'd been able to sample an infinite number of times, we would have had an infinite number of very narrow rectangles, and they would have filled this space in blue perfectly, because they would follow the curve perfectly, because we'd be checking the velocity an infinite number of times. So we found the green area, we wanted to find the blue area. One or two, if that makes sense. That's why our computation is wrong. That's why it has an error. Please, point.
So why would the test makers, or just people in general, use like one irradiance sum over another, like a left or right or whatever, because it would just completely change like our answers anyway.
True.
Like if it said like use the right one, like as I'm drawing the left one on the graph, it's just like there's so much area that like goes above and below and that doesn't, fill in the graph exactly, But if I use the right irradiance sum, it might like, be completely different.
I'm going to give you kind of a short answer, 2 points for asking. And then as we move on, don't hesitate to ask again. Your question will be easier to discuss once we've gone a little further into the packet. For the purposes of the AP test, they want you to understand that for some simple functions, this is a bit complex, for some simple functions, you can declare the left to be an underestimate and the right to be an over. And therefore, you know for certain that the actual answer is in between. There have been a few AP test questions that require you to know that. The midpoint and trapezoidal tend to be actually pretty close to the actual.
Oh, okay.
So that's kind of a quick answer for our test, but
Okay.
in a real life situation, it gets a lot more complex. So, good question. Anybody else? Cool. Okay, any questions about like what we're looking, like it's important that you can visualize it. The visualization is not just hey, this is kind of cool. It's like you'll be tested on it. So make sure that makes sense.
So if we were doing a right something, would the red rectangles be above the line? Like how would you draw that?
Hold that question for a second. We're almost there.
Okay.
2 more for Maddie. Okay, go to this one now. Right here. Okay, we have been discussing something that is officially known as the fundamental theorem of calculus. The wording should give you some sort of sense as to the importance of the idea. Okay? I went through the AP test once and I counted how many points can be earned by thoroughly understanding the fundamental theorem. You had to understand other things as well. But if you didn't understand the fundamental theorem, you would have not gotten those points. 1/3 of the entire test deals with the fundamental theorem. 1/3, okay? This is not the fundamental theorem. This is an application of the fundamental theorem. So we will show other applications in the future, but we start with this because it's a little bit easier to wrap your head around. This is all we've been discussing now for 2 class periods. There's 2 ways to calculate displacement. One way is by simply comparing 2 positions and then subtracting them. That's displacement. Remember, don't think of equal as meaning something becomes something. Equal means these 2 things are the same. We've just been talking all day today about that idea, that the other way to calculate displacement is by calculating the integral of the velocity. That's what the fundamental theorem says, exactly what we've been saying. Just like we did here. We can calculate displacement by simply comparing positions, which is what we did. I lost my notes. There we go. What we did here. But we can also calculate displacement by integrating velocity. So that's the fundamental theorem. Right there. Questions? Please, there you go.
I guess just on the last thing, like is what we did on the graph, is that all we have to do to that? Just like the first one? You just do like the 7.
Oh. This
Like-
one here?
Yeah. Well, no, I mean like when we did the graph, like do we do all of them or is that it?
Oh, gotcha. I'm sorry. Like this part here.
Yeah.
No, you would keep going. I apologize
Okay.
for confusing you there.
There you go.
So then we would draw this one, which would look like this. Does that make sense?
Yeah.
2 more for Reagan. Sorry about that.
2.4.
Oh, so my brain stopped working. 2.4. Thank you.
Good name.
Like that. Please, Zach.
So I noticed on this graph that the last one doesn't really like portray where the graph goes, like the last rectangle. Could you, instead of having everything by 10, could you at the end say like 2 5s?
You can do a more sophisticated computation. They won't necessarily ask you to, but you could, for sure.
I mean, like, could you do 3 10s and then 2 5s?
Uh-huh.
Okay.
2 points.
Okay, so what does the 234 miles mean?
I'll get you to answer it yourself, then it'll stay in your brain better. If the plane has a velocity of 7 miles per minute, what does that mean?
Well, the velocity is 7 miles per minute.
What does that mean?
Every minute it's moving 7 miles.
Perfect. So if the plane does that for 10 minutes, what's going to happen?
Okay, move 70 miles.
Does that make sense? So this is going to be 70. So what we're saying, Jonah, is that for the first 10 minutes of the 40-minute period, the plane had a displacement of 70 miles. Then for the next 10 minutes, what's the displacement?
150, okay. Sorry, 95.
95. What's the displacement for the next 10 minutes?
45.
Next 10 minutes?
24.
We add them all together, what do we find? Does that make sense?
Yeah.
So what does the 234 mean?
The displacement.
For the what time period?
0 to 40.
Perfect. Does that make sense?
Yeah.
Does that answer your question? Perfect. The 234 is the displacement for the entire 40 minutes. It's an estimate, but that's what it means. Good work. Okay? Go back to here. Reagan, did I get your question?
Yeah.
Okay. Go back to here. Okay, fundamental theorem. Okay, it's a really, really simple idea. Don't make it complicated. Look at me. This is the equation you start with. Okay, that's what we've been talking about. If I integrate velocity, that's the same as taking the difference of two positions. But you can rearrange that equation any way you'd like to find other things. Because that equation is nothing more complicated than A is equal to B minus C. So for example, if I want to isolate B, all I do is add the C across. And then switch the sides, so you get this. Okay, show me 1 or 2 if that makes perfect sense right here. This. 1 or 2 if that makes perfect sense. Oh, sorry, talk to
Can
me.
you say again?
Huh? No worries.
Sorry.
Can you see, Kayla, that this A equal B minus C is really the same thing as this? I've got this is the same as, this minus this. You good with that? So all I'm saying is that if we need to, we can rearrange.
Okay, yeah, okay.
So you're good. 1 or 2 for here. Show me. 2 points for the room. But B is just the position at time 40. B is simply the position at time 40. So the position at time 40 is going to equal the position at time 0 plus the integral from 0 to 40 of the velocity. So by rearranging the fundamental theorem, I found a way to calculate where the particle is located at time 40. Please.
Are we going to have to find the distance of Earth?
The distance traveled?
Yeah.
We will eventually. 2 points.
Would we have to use this theorem right here?
Similar,
Okay.
but not quite. It's very good. 2 more. Please.
Why is this the fundamental theorem of calculus? Like, why is it like so grand?
Oh, in my opinion, it's because it does what Kayla asked about, and I think you asked about it as well. That's how we actually connect the method of multiplying and adding up an infinite number of terms to the magical method of like, oh, we don't have to do that.
Okay.
Because these two things are the same.
Okay.
Hence why it's so fundamental. It connects derivatives to integrals.
Makes sense.
Anybody else? Don't pack up. Look at me. Oh, please.
So you have this written like the equal sign. It's not an approximation, but wouldn't it be approximate because it's an integral?
Oh, listen. Hey, look up. Come on. Don't leave. The integral itself is not an approximation. The integral is perfect as long as we could add up an infinite number of terms. When we use a Riemann sum to find the integral's value, we are approximating the integral's value. So this equation is a perfect equality. They are perfectly the same as long as you can calculate the integral perfectly. We just haven't yet figured out how to do that. Is that okay? Perfect. Anybody else? Awesome. You can also rearrange the other way. You could write this. S of 0 is equal to S of 40, don't leave on the bell, minus integral from 0 to 40 v of t dt. You can also do that. Give me one or two if that makes perfect sense. Show me. Listen close. You actually have learned enough to do quite a few things in the packet. However, we have not discussed everything you need to do everything in the packet. So this is not yet a homework assignment. If you choose to start working on it, there's no harm in that because you can do a lot of it. But if you want to wait, that's fine too. We'll finish talking about it on Monday. So, good job. Good work.
Oh,